Hi, I'm Joel Sokol, Harold E. Smalley Professor in Georgia Tech's H. Milton Stewart School of Industrial and Systems Engineering and founding director of Georgia Tech's Master of Science in Analytics degree. In keeping with today's theme, here's my background and career path. I started off in college at Rutgers University with no idea what I wanted to do as a career. I bounced around from major to major at least 5 times until finally in my junior year, one of my roommates convinced me to take a course with him. There's a lot of math in it. I think you'll like it, he said. It turned out to be an optimization course, and after the first week, I was hooked. I wanted to build optimization models for everything, starting with my fantasy baseball team. I really liked the companion stochastics course too, so I decided operations research would be a good career for me. But operations research was not an undergraduate major at Rutgers. So, based on how I could optimize the courses I took, subject to the constraints and loopholes and the graduation requirements, I ended up with majors in math, computer science, and applied sciences and engineering. I went on to get my PhD in operations research at MIT, where I was again undecided about my career path. So I interviewed for all sorts of jobs, academic jobs in engineering, math, and business schools, industry jobs in applied research and telecommunications, logistics, and others, and even a think tank job. I decided to take the offer that seemed most overall interesting and flexible. And in the end, I picked joining the faculty at Georgia Tech in the School of Industrial and Systems Engineering, though it was a close call between that and the think tank that was 3 blocks from the beach. And I've been at Georgia Tech for 24 years now. Georgia Tech is my first real full-time non-internship employer, and it might well be the only one I ever have. There are a lot of great things about being a professor. I really like teaching. I really like thinking through interesting research ideas. I really like the time flexibility that being a professor allows. And I've had a great group of colleagues to work with for all 24 years and counting. But there are two other great aspects of being a professor that are most relevant to my talk today. First, I have the flexibility to turn my research and teaching activities in whatever direction I want. So although I started as an applied optimizer, both my research and my teaching have moved more in the data science direction. And second, I also have the flexibility to work on outside consulting projects, like the one I'm here to talk about today, that I've been working on with Gurobi, a free online optimization course targeted to data science professionals called Introduction to Optimization Through the Lens of Data Science. It's a basic optimization course, but one meant to be especially accessible and helpful for data scientists that can position them to be able to create and solve optimization models on their own. So here's what I'm going to be talking about today. First, why? Why create an optimization course for data scientists? And then I'll talk about what's in the course, with specific emphasis on what's different about this course from other optimization courses that we might all be familiar with, including some examples of how we present material and what we give the students to do. And now, as I say in the course, let's go ahead and get started. So why create an optimization course for data scientists? A simple answer would be, there's a lot of them, especially compared to operations researchers and optimizers. The Bureau of Labor Statistics already classifies more people as data scientists than operations researchers, and that number keeps growing significantly. And not only are there a lot of data scientists, but let's take a look at how Informs describes operations research and analytics. Transforming data into information, transforming information into insights, and making better decisions. It's a nice sequence starting with data and ending with better decisions. The first two of those are usually analytics/data science tasks, and any data scientists are usually trained to do both of those first two things. Any good data science program, including Georgia Tech's, as well as any good program of self-study, which is how many data scientists acquire their initial skills, teaches students how to start with data and use data science techniques to end up with insights. But only a few of them teach the last step, how to take the information and insights and use them to make better decisions. And that last step is often done with optimization. I talk with a lot of data scientists, and a lot of them realize that they're missing optimization knowledge because only a fraction of data science degrees teach optimization. Usually only ones like Georgia Tech, where the degree's creator has a background in optimization and/or operations research before getting into data science, which means that most data scientists are missing that last important step. On the other hand, although many data scientists realize they're missing optimization knowledge and say they'd be interested in learning if it's not too painful or difficult, most of them don't realize the value they're missing. And that's where this course comes in. Part of our task is to demonstrate the value of learning optimization, and that because most data scientists are missing optimization from their toolbox, the ones who do have some optimization background can really use it as a differentiator. This course is meant to do that. We position optimization as an extension of the standard data science toolbox. In many cases, the outputs of data science models serve as inputs for optimization models. From the point of view of optimizers, that's something we've had to work with our whole career. Do we need to optimize production and inventory in a way that meets demand at minimum cost? Well, then we better have a good way of forecasting demand. Are we trying to find the quickest route to deliver a truck full of parcels around a city? Then we need to have good predictions of what traffic will be like throughout the day. Is there a set of jobs we want to assign workers to in an optimal way? That means we have to have good estimates of each worker's ability to do each job. I could go on, but you get the idea. As optimizers, especially ones with as much gray hair as I've got, in the past, we've often had to estimate or make possibly not entirely realistic assumptions in order to get input data, and then hope that when we optimize, the data is good enough. The data science revolution really opened up a lot of great doors for us. Suddenly, we were able to get much better estimates and forecasts to use as input data, and as a result, the output of some optimization models has gotten a lot more valuable. But for data scientists coming from the other direction, most of them haven't been trained in optimization. So for those data scientists, this course will help them gain that missing tool and bridge the gap between information and insights and decisions. And there's also a benefit to employers of data scientists. This course will allow their data scientists to add even more value. Here's a snippet from the course where I talk about that.
Hi there, and welcome back to Introduction to Optimization Through the Lens of Data Science, brought to you by Gurobi Optimization. I'm Joel Sokol, Director of the Master of Science in Analytics degree at Georgia Tech and a professor in Georgia Tech's Stewart School of ISYE. In a previous lesson, we saw some optimization success stories. There are lots of others, and in this lesson, I'm going to tell you about some more. As with the previous lesson, these are all collected and published by the professional society INFORMS, the Institute for Operations Research and Management Sciences. The first example I want to mention in this lesson is Turner Broadcasting. Given a set of television advertisements that they've been contracted to run and a set of TV shows that are airing on Turner networks, which ads should be run at which times on which shows? There's a lot of data science in the background, predictive models for estimating audience sizes and types, because different ads are targeted at different people, and Turner wanted to maximize the target audience delivery of its ads because that would give advertisers more value. Turner would then be able to charge the advertisers more. This is an example where the optimization model sits on top of data science models, and the overall value is from a combination of data science and optimization. Without good data science models, the optimization model would be optimizing in the wrong direction, and without good optimization models, the data science model could make predictions, but the company couldn't make the best use of them. Both are needed, good data science models and good optimization models.
So now let's see what's in the course and what's different about it. The course has three main parts: motivation, modeling, and cases. Hopefully that seems reasonable, but usually there are a couple of questions that come up at this point. First, modeling without a way to solve models isn't going to help data scientists learn to use optimization. If you are thinking that, I agree with you 100%. But in this course, the software is part of the modeling. As I'll show later, we present models in three parallel columns: an English statement, an algebraic model, and Gurobi Pi code, which, if you're not familiar with it, is Python code that calls Gurobi optimization libraries. The idea is to help people think of models in three parallel ways, so that eventually they might feel comfortable enough to just sit down and write Gurobi Pi code without needing the intermediate steps. I'll show more about this later. But first, let me answer the other common question. Where's the optimization theory? Let me tell you a quick story. When I was an undergraduate, I took an optimization course from the industrial engineering department at my university. The course started out with a question. Given a very simple situation, how could we write and solve a mathematical model to find the best thing to do? Although the course did eventually cover some basic theory, things like the simplex algorithm, network algorithms, and branch and bound, most of the course was about how to build optimization models of real situations. I loved that course. In fact, that was the course that convinced me I wanted to go to graduate school and do this stuff for a living. And I started seeing optimization models all around and using them in my summer job, my fantasy baseball league, and more. On the other hand, when I got to graduate school, the first semester PhD optimization course I took started off with the words, okay, suppose we have a separating hyperplane. It was a very different type of course, almost entirely about the underlying theory of linear programming. I really enjoyed it, and I used it a lot in my PhD thesis, but looking back, I didn't use separating hyperplanes or extreme point theory in my summer job or my fantasy baseball league or anywhere else in my life that I was still solving optimization models. This course is designed to teach data scientists to use optimization. Optimization theory is great, but because the purpose of this course is to get data scientists building and using optimization models, to convince them it's valuable and then help them learn to do it, the focus is almost entirely on modeling and getting solutions. If people take this course and get so interested that they want to learn the underlying theory, that's a good outcome too, but that's extra. We just want to get data scientists to use the optimization the same way they might use any other data science tool without knowing all about the underlying theory of it. So in this course, we'll cover just a little bit about optimization theory, classifying models, including very basic convexity, and a very little bit about how most optimization algorithms work in general. So let's go back to the three parts of the course: motivation, modeling, and cases. First, there's the motivational part, which actually has two pieces: optimization as an extra tool for data scientists, and optimization as something that data scientists might not realize they're already doing. So why should data scientists learn about optimization at all? In this part of the course, we rely on some of the one-page case studies that Informs has published on its website, many of them taken from the Edelman and other prize winners and submissions. There are lots of great examples of optimization success stories, from routing trains around the country and ships around the world, to scheduling television advertisements and scheduling surgeries and scheduling sporting events, to pricing housing, sourcing raw materials, generating power, matching kidney donors with recipients, designing floodwater handling systems, and many others, all describing situations where optimization has saved lives and/or made a difference of many millions of dollars to a company or organization. In many of those optimization success stories, optimization sits on top of data science. Data science was required to determine inputs that an optimization model then used, and together they created much more value than either one would alone. But we also mentioned some instances where optimization stood alone to make sure they know that there are times when optimization by itself can be a very valuable tool, just like sometimes data science models by themselves can be very valuable. The second part of the motivation is technical. There are so many data science models that have optimization under the hood that aren't made clear when the models are presented in a data science course. Multiple linear regression is still the most used data science methodology, and as optimizers, we know that it's just an easy case of convex optimization. Variable selection methods like lasso, gradient boosting approaches, random forests, time series models, deep learning, all these and many more have optimization under the hood as the engine that drives the model. This course isn't about the mathematical theory of optimization, so we don't go into detail, but we demonstrate how the basic questions underlying many of these data science approaches are instances of constrained or unconstrained optimization. And we build on that to show how, in some cases, understanding optimization can help a data scientist customize standard data science models for special use, adding constraints to a regression, for example. All of these are accompanied by real examples to bring home the point that optimization not only can extend a data scientist's capabilities in valuable ways, but that optimization can help make someone a better and more valuable data scientist. Next up in the course is the modeling section. Unsurprisingly, that's the largest part of the course. And it's also the hardest part of the course to target because there's such a wide range of people with data science education. Our goal in this course is to try to meet everyone wherever they are. Coding-wise, Python is by far the most commonly used and most commonly taught language for data science. Just about every data scientist will be proficient enough with Python to be able to combine basic Python code with specialized libraries. So all we really need is to teach the specifics of the Gurobi Pi library. But when it comes to modeling, the situation is very different. Some data scientists are already fairly proficient with taking real situations and describing them mathematically, but there are lots of others who have very little background and need to start at a much more basic level. So we try to meet each student at their own point of entry. We provide modeling lessons starting with the very basics all the way up, and students can use just what they need. For students who need it, we start at the very beginning. Things like if B is the number of copies of a book that were sold and C is the price each copy is sold for, then B times C is the total revenue from selling the books. In fact, we even start a little earlier. From a modeling perspective, there's actually a step before this, starting with the question, how much revenue did we make from selling this book? And realizing that we need to know how many copies were sold and what the price per copy was, and creating notation like B and C. So we start there and go through the basics. And we go on from there to more complex situations, subscripts, summations, sums of products, multiple summations, etc. And at each step, we give a set of exercises for students to practice on. And at each step, we let them know that if they're already proficient, they can skip this lesson and the exercises and move on quickly to the next. But for the ones who need it, these lessons help them get up to speed quickly. At this point, I have to give a hat tip to Morton Lewitt, one of my undergraduate professors who wrote an excellent book teaching the C programming language. The best part of the book to me was how he dealt with C's very flexible but potentially very confusing variety of operators and operations. At the end of the chapter describing them all, he wrote 100 exercises, each one a tiny snippet of code stripped to its minimal fundamentals, and asked us to determine the output of the operation or operations involved. The exercises started very simple and straightforward and then quickly built up to more and more complex. But it was very inductive. If you knew how to answer the first K exercises, you were able to answer the K plus first, which just built up from the first K. And it was a great way of helping students quickly scaffold from the basic to the complex. That's exactly how we approach these basic modeling exercises. We couldn't quite do it as efficiently as Professor Lewin. We needed over 130 exercises instead of 100, but that's exactly how they work, to help even students who need to start at the very beginning progress relatively quickly to expressions like multiple summations of products, summations over sets, etc. Here's a quick video clip of what the introduction to the course is like.
In this course, you're going to learn the fundamentals you need to start using optimization, both by itself and in tandem with data science. You'll see what mathematical optimization is, how, whether you're already a data science professional, an amateur, or even if you're still a data science student, you're already using optimization under the hood of many standard data science methods, how to use optimization to customize data science methods when the basic approach isn't quite what you need, and how you can use optimization either in tandem with data science or on its own to answer a really wide range of real-world questions that data science on its own isn't equipped to handle. Along the way, you're going to learn how to use state-of-the-art optimization software, the Gurobi optimization Python libraries called Gurobi Pi. You'll see how to build Gurobi Pi optimization models for real-life situations, and you'll see some different ways of writing Gurobi Pi code that will help you find your own personal style. As we go through the course, you'll see how to take English statements and requirements, write them mathematically, and code them in Gurobi Pi using this 3-column format that shows all 3 ways to say the same thing. And at the end, you'll see some case studies where you'll get to embed data science models and Gurobi Pi optimization code together in Jupyter notebooks. So welcome to the course. Let's go ahead and get started.
The introductory lessons and exercises are also where we first introduced the 3-column format of English, math, and Gurobi Pi. I have enough gray hair to remember back in the days when spreadsheet optimization in Excel was a hot thing for business school students to learn. At the time, I remember a lot of faculty complaining that the students believed the Excel sheets with its changing cells and target cell was the model, and therefore the students didn't even learn the real model, which by that they meant the algebraic statement of the model. But for this course, we've thought about that issue a little differently. Whether it's Excel or Gurobi Pi or something else, We believe that code or software input that will return the optimal solution really is a valid model of a problem. In fact, in some ways, it's a more useful model than the algebraic model because it can return a solution via the software, whereas the algebraic model is more familiar to us as optimizers, but it doesn't return a solution unless we translate to a different form. So whenever we're demonstrating a model or asking students to write a model, we include both. The algebraic model is important because that's the language that most optimizers speak. Data scientists need to know how to express optimization models algebraically so they can communicate with optimizers. And the Gurobi pi model is important because that's how data scientists can find solutions to their models. So students need to know how to write a model using algebra and how to write a model using Gurobi pi. And that's not all. We also believe that having an English model is also valuable. It's important for communicating with owners and stakeholders of the decision being made. Showing a math or Gurobi model won't be very helpful for many of them, but an English description can be very helpful for discussion to make sure that the model is a good reflection of all the important aspects of the real situation. It's also helpful to have the English model in order to make sure that everything's correct in the algebraic and Gurobi pi models. At least that was our original idea. The English model is important because it helps you talk with non-technical people about the situation. The mathematical model is important because it helps you talk with optimizers in a common language. And the Gurobi pi model is important because it helps you get solutions and do analyses. But since ChatGPT and large language models in general burst on the scene, there might be another use for the English model. It might not be so long before LLMs can pretty reliably take English models and write algebraic and Gurobi pi models for us. So all three of these models are important, and we want students to learn them all. And here's what it looks like in the three-column format, with the English model on the left, the algebraic or math model in the middle, and the Gurobi pi model on the right. Here are some examples, all taken from different examples in the course, so don't worry if they don't look like they match up. You're right. Here's one at the basic modeling exercise level. On the left is the English model, written in regular English without any sort of notation. In the center is the algebraic model, and on the right is the Gurobi pi model. Here in the basic exercises, the Gurobi pi model is really just Python in most cases because we're not optimizing anything yet. But here's an example of an optimization model's objective. And here's one with a couple of constraints. As you can see, everything lines up horizontally. It's the same objective across the row in English, in math, and in Gurobi pi. And in the constraints, it works the same way. Here we have two constraints, and each one lines up across the row. So it's easy to see how the three models, English, math, and Gurobi pi, all correspond to each other. And by the way, of course, we include data and variable definitions in this format too. Here's an example of a full model, really three full models, English, math, and Gurobi pi, for a simple problem. You can see the three columns, English, math, and Gurobi pi from left to right, and the four main parts of each model separated by row, data, variables, objective, and constraints. Everything lines up nicely from left to right, so it's easy for students to see how the English, math, and Gurobi pi all correspond to each other. And here in the upper right, because it's unique to the Gurobi pi model, we include the setup code, importing Gurobi pi, defining a model object, and opening the data file. Of course, we don't present this model all at once. We talk about each element separately, highlighted in all three columns next to each other. As each part of the model is presented, it's added to the slide in a different color and talked about. So unlike this model, where new things are popping up every few seconds just as a demonstration, in the course, the model will get built up over the course of an entire lesson, or even sometimes more than one lesson. So by the time the model is on the slide in full, it's all been discussed piece by piece, and it doesn't look super dense like it did when I first put up the entire model for all of you. We can also use this three-column format to help show students what's different between types of models. For example, integrality restrictions are traditionally grouped in with constraints in an algebraic model, but in Gurobi pi, they're part of the variable definitions. So when the restriction to binary variables is presented, we highlight the relevant part of the Gurobi pi variable definition and point out how they relate to each other. The first model I showed you is a pretty small one. Here's a larger, more complex one. When we get to the largest models, like this one from one of our case studies, the Python and Gurobi pi data handling would take up too much space, so that gets handled in a separate file. But by this point in the course, the students have seen a lot of other models, so they already know what those parts of the Gurobi pi model will look like. And even so, this model is large enough that I need to show it to you on 2 slides. Here's the data and the variables, and here are the variables again with the objective and constraints. In fact, this model is actually color-coded, so students can see how it's a combination of 2 optimization archetypes that they'll already have learned in this class. They'll see that the red model is a diet problem archetype, and the black model is a network flow archetype, multi-commodity network flow to be exact. And this case shows how the 2 archetypes can be combined to help the World Food Program effectively feed more people in need around the world. And the 3-column format helps them see how the English, math, and Gurobi pi of it all mean the same thing. Using this 3-column format, we cover basic optimization modeling, but we also want to cover other aspects of the optimization process. We spend a lesson discussing recursive looking constraints like this one. Here's a linear constraint where a variable is defined to be equal to a function of itself. This sort of thing is more difficult for data scientists who have computer science or programming backgrounds especially. They're used to recursion requiring an additional function or more analysis, so it's well worth a lesson to explain that in optimization modeling, we can write a recursive looking linear constraint as is, and Gurobi pi does the underlying work necessary to handle it. We also include lessons on using optimization for sensitivity. We don't go into the theory, but instead we focus on the ability to ask what-if questions and to modify a model's input data as conditions change without needing to modify the model itself. We talk about rolling horizon models, where the output of one model is the input to the next very similar one, and about creating models that can be used with different data sets, not just rolling horizon and what-if questions, but also models that might be used each day with that day's specific data set, or each year, or each fraction of a second. In all those cases, using the same model with a different input data set is much easier than building a new model every time. We talk about substitution and how there can be more than one way to write a model, including having more or fewer variables. For example, where any 2 of 3 sets of variables can define the third set through equality constraints. But when substituting, it's important to substitute also in the non-negativity constraint, or else the model might return a solution that shouldn't be allowable. We have lessons to deal with all these sorts of issues and more, always based on example models that demonstrate the lesson specifically. We even discuss developing an optimization model from a real-world situation and how there's often a lot of back and forth involved, making sure that we have a model that correctly reflects the real situation, and how if our optimization model gives us nonsensical results, or is even infeasible at a time that it shouldn't be, it's very likely to be a bug in our model rather than an issue with software or even with optimization itself. And we spend several lessons on modeling with integer variables, especially binaries, and how to use binary variables to model logical constraints and conditions, building up again from simple to complex and introducing extended column truth tables as a tool to check whether a constraint is working the way you want it to, and to identify what case or cases are causing problems if not, so the constraint can be modified or an additional constraint or constraints added. This section is really like a miniature version of the modeling basics, where we start with simple relationships and simple exercises and build up to complex compound conditions and exercises. After a few lessons and a bunch of exercises, they're able to build up the basic concepts to write mathematical and Gurobi pi constraints for more complex conditions, like this one. Here, they need to combine 2 algebraic or Gurobi pi constraints, one simple and one more complex, to match the single compound statement in the English model. This sort of scaffolding of concepts has already been used in the classroom and it works well. And with the truth table, they can see how all the possibilities that are allowable satisfy both constraints. And of the possibilities that are not allowable, some fail one constraint and others fail the other constraint. So together, these constraints match the English. Finally, at the end of the modeling section of the course, we spend time demonstrating common model archetypes, things that come up often in practice either by themselves or more commonly as building blocks for more complex models. Knowing these model archetypes is also helpful when talking with optimizers who've probably studied them too. So we cover basic models like knapsack, covering, diet, cutting stock, packing, network flow, shortest path, assignment, and generalized assignment. And throughout the modeling section, we show lots of different types of applications and situations that optimization can be used. For that, I have to give a tip of the hat to Professor Wayne Winston, whose introductory optimization textbook has always been my favorite because of the hundreds of modeling examples with such a huge variety. We've tried to duplicate that spirit in smaller scale in this course. The last part of the course is case studies. Case studies are a great way to show optimization in action, as well as to show how to combine multiple concepts from the course into a larger and more complex model. And two of the cases really show how much impact optimization can have when combined with data science to address important problems and questions. In all of the cases, in addition to the 3-column, 3-model format, each come with Jupyter notebooks to combine the data science and optimization. Each case's notebook comes with a large data file, as well as blank areas for students to fill in the data science pieces and the optimization pieces. The first case is an artificial one built around Gurobi's burrito game. Having gotten to try optimizing by hand with the game in the first module of the course, students now at the end get to use what they learned in the course to get optimal solutions to burrito game instances. The second case comes from a research paper that deals with electric power generation, optimizing power generation sources and levels every few minutes in order to find the best trade-off between power generation cost and the cost of health impacts from emissions. This paper was a collaboration between 6 Georgia Tech faculty from 6 different departments, and as inputs to the optimization model, this research required not just data science models, but also economic models and complex atmospheric models. So it really highlights how optimization can pull together the outputs of lots of other models to help make the best decisions. Of course, we don't expect students in this course to build complex atmospheric models. I couldn't teach them because I sure don't know how to do that either, so they're given the outputs from those models in a data file. The final case is based on the World Food Programme's use of optimization to make its food purchase and distribution plans in order to feed as many needy people as possible. This one too requires predictive data science models as input, so the Jupyter Notebook contains space for students to try both the data science modeling and the optimization modeling. We also show a lot of what-if analysis that really shows the power of using optimization not just for initial decision-making, but also for dealing with trade-offs and what-if analyses and reacting to changing conditions on the fly. The models can get large enough that only people with a full Gurobi license, either a commercial license from their company or the free license Gurobi offers to all academics, can run them. But people without either of those still have access to a license that can solve models with up to 2,000 variables and constraints, so we provide smaller data sets to allow those students to run the models too. So that's the gist of the course, Introduction to Optimization Through the Lens of Data Science, coming to a data scientist near you later this year. But before I open it up for questions, I want to say a few thank yous. I'm the one who gets to give this talk and to be the face of the course and the lessons, but there are a bunch of people at Gurobi who've put in a lot of time and effort and expertise and ideas to help make the course work well. And I want to make sure to thank all of them, in alphabetical order. Malia Aramon, Juan Antonio Orozco Guzman, Lindsay Montanari, David Torres Sanchez, Rahul Swami, Jerry Yurchison, and Yuri Zinchenko. And now, please feel free to ask me any questions you have.